안녕하십니까. 공예작물학 시작하도록 하겠습니다. 공예작물학 영어로 해야 되는데. Hello, I industrial plant class started. Um, to open up the Jupyter environment, I will open iPlant and Jupyter lab allow root. So last week we actually created the network of Arabidopsis thaliana using fixed strings, which is extracted from the blast result. So the blast result is coming from the blast result is coming from the blast against. The query was that the already known promoter sequences from Arabidopsis, and we blasted against to the laboratory genome, and we extracted the short sequences that actually exactly matched with the promoter sequences, and we considered that promoter sequences as fixed string to count the numbers. So allow. So what I'm trying to show you guys is that we can create our own database based on certain fixed point of observation. So we created observation point that was the fixed string. I think this is better for recording my voice. Actually, I heard it. It prevents certain not present sound. Okay, what was that? What was the? This was the file that I created last time. Okay. So I will re-update the result. Done, done, done. So we created the block selected, and we can see what was our point of observation. So this is the point of observation. We are counting how many of these, and how many of these, and how many of these in Arabidopsis thaliana upstream sequence. So we are extracting the sequence from Arabidopsis thaliana in this way. So actually we are doing this analysis my own laptop to show you that majority of the analysis can be done in your laptop. So I will show you my computer spec briefly. So Intel Core i5, so not that bad but not that good, and my memory is 8 GB, so it's not that bad and not that good. So this is average spec of recent laptop. So you can check your computer spec by yourself and compare with mine. And we are counting the features using these features to count data frame, and it will collect the numbers in this way. I'm thinking it will not take so much time, or it will take a lot of time. I think it will take a lot of time, so I spent a lot of time for this. So I will so we saved, right? So we saved this file in this way, and I will run it. And the shape, okay, almost similar. So actually I saved in a CSV file, so it count index also, so it increased from 501 to 502. And so I will update the index, and the shape is again 501, right? And I created the Tiffany profile from this matrix. So this became 27,000 to 2. Okay, hold on. Okay, so what we did was we constructed this matrix. So let's check the matrix. So matrix was in this way. So we tried to check the composition using cluster map, but it took a lot of time, and we just gave up to see the whole picture, and we made this Tiffany profile and PCA profile using this command, and we extracted these pictures with k-means, and we saved the result of Tiffany in hold on, in this way. So we have this Tiffany PK. For this analysis, the reason why I saved was that it took a lot of time to calculate the Tiffany profile. So I will recover the Tiffany information by lead picker. So I save with picker. So now we can redirect this information. So we already assigned the result of k-means. So we can briefly see what kind of cluster we have. But as you can see, this cluster is not so rigid. But this class may be reasonable, but I don't think this is really good clustering. So I made last time. What was that? So we use the profile of certain gene, right? So certain gene profile. So maybe this was the what was that? I forgot. I remember that was knock. I don't know. Knock transcription. Sorry. Knock transcription factor. That what I'm remember. No, not transcription factor, right? So it was not transcription factor. So we could retrieve the nearest not transcription factor using this we retrieve the profile, right? So we can see the profile of this not transcription factor. So not transcription factor has the t-SNP profile. First t-SNP profile is 4 and 55 as the second t-SNP profile. So we can subtract the profile for all information. So all information. So we subtract. So which means we just minus it, right? So we minus it. So we minus this profile, and we say so power. So power. So square it and sum it. So what this mean? What is the meaning? So I will explain more. So this is not transcription factor, right? So this is not transcription factor, and it has this profile. This profile. Then what is the nearest profile? Of course, it's self, right? So but I want to calculate it. So I minus it. And also I want to minus it. Of course, this will be 0. So 0. So nearest 0. We try to find the other gene which is nearest to 0, right? Which has a minimum difference between this original profile of not transcription factor. So we extracted the value, and we saved in this ed, right? So first one was not transcription itself, so it becomes 0, but the other is like a lot. So what we want to do was that make a histogram. So I try to limit the histogram which has less than 100 and see, right? So the value was in this way. So there are so many genes that shows less than 20. So it is still a lot more than 200. So we sort using AlgoSort. So AlgoSort will show you the order returning the index. So what is the meaning? So if you have array, so example, if you have array 1, 5, 4, 2, 1, 5, 4, 2, 3, right? Now AlgoSort example. So what is the meaning? So the order is sorted. So 1, 2, 3, 4, 5. If it is sorted in this way, 1, 2, 3, 4, 5. So the index is the return by AlgoSort. So the first one should be 0, right? So second one should be third one. 1, so 0, 1, 2, 3. Third one should be here. Fourth one should be here. Second one should be here. And first one should be here. Right? So this is the AlgoSort work, the how AlgoSort working. So it return sorted index. So we limit the sorted index from 0 to 10. Okay, so 0 to 10s. So these indexes the genes that is closely related to NOC transcription factor, right? So this was the genes. So after driving this information, so why so index is not defined, and we can retrieve the cluster. So cluster 17. So the based on the k-means, it shows everything is cluster 17. Everything is cluster 17, and we can see the profile, not t-SNP profile, original profile by this way. So feature to count. So we can limit the feature to count. Right? And yeah. So this is the profile. So everything here a profile for each genes, and we can see, okay, these genes having similar profile. Interesting, right? So let's run it, and we will see same picture. And I don't want to have in this way, so I will change figure size 가로 10 0 5. Okay, then we can see 3 will be more informative. 20, we can make it 20. Good. Then it will show you more informative way, but I don't want to see this weird long conserved promoter. So this is very interesting. This is actually conserved promoter. Must be some function, right? I know. Anyway, so let's make it just 50. Good. Maybe I want to change this one later. Okay. So last week, what I wanted to do was that what was that? I will remove this. Was that this is not transcription factor, but the other is not transcription factor. So, so this is all TEL10 information. I want to retrieve the annotation of TEL10. So let's go to ensemble is I love it because no ensemble no to download, yes this is the one. So out of Italiana we already download the file, but here it has annotation. So where is the annotation? So annotation would be I don't tab separated file contains selected data for individual species and comparative genomics. No. This file annotation. This file contain annotation. I will download this one. What is EMBL? So I will use this one. I will use this one. Okay. And so this is the one. Let's download it. So you already know how to download, right? In this way. So it is downloaded, and of course we can retrieve the file using pandas. So what is the name? Arabidopsis GTF tab and comment shop, and we don't have a header. Let's see what happened. Hey. So using this data frame, we can retrieve the annotation. So what is the annotation? We can check. So this must be the annotation, I think. I don't know. So let me check. So first one. So gene source is Araport 11. I don't think this is annotation. Did we? Okay. I will retrieve. GFF first. Okay, this also contain information. It looks like, but in this case, it just contain gene information. So must be more. No. Then I will not use this one. I will use just the GFF file. And we already retrieved genes. So I will make mRNA. GFF. Okay, to equal mRNA. Then it will give you in this way, and I will first apply lambda x info. Maybe I already info parse x and what I don't know. Let me check. 8 and 2. Okay, so these don't have any information. We have to extract gene. no, gene, and so we will run it, and I will check gene what. So first one. Okay. So these contain description. So I will extract the name and description. Okay. So I will extract the name and so name I will put it, right? What? Parse X and name. Why it don't have in this way, in this case, and I have to get name X. So I really want to have some except function in the apply or lambda. Oh, let me check if lambda has exception. Python lambda have exception. No. Lambda Python lambda function range exception. Define another in the range exception. Okay. No, this is not cool. So I will not use that way. So I will just return. I will just use the definition. So try. So I really what I was wanting to was that hopefully it has try and accept here. Return none. So I will use in this way. So good. Right. So and that description. Description, right? Description. Desk. Good. And now we have table that has information, okay, and also we have to add ID also. ID 누가 ID and what is that? ID, right? ID. I don't want to have that gene dot colon. So replace the gene colon. Then now we have this matrix. So just limit this table in this way: ID and name and description, and this will be not. So regardless the result of this analysis, you guys actually learning how to make your own information table from public data. So actually the public data is not the kind for you guys to use. So this is really essential technique you guys have to learn. So now we have table, and I will save it to picker and Arabidopsis annotation pk. Okay, good. Once it is saved, I always comment it out, avoiding some unwanted overwriting of existing file. Okay. So what I want to do was that is the candidate gene profile, right? So candidate gene profile, and let's remove everything. Undo. Remove everything, and this was candidate gene, and the candidate genes can be retrieved, and I don't want any .1 like mRNA isoform index, so I will remove it. Good. This is the candidate gene, NIX, and I will I want to index it, annotate, set index by ID, right? Then X. Cool. So now we have associated gene based on the what was that? Promoter profiling, right? So knob is the main guy. Knob is the main guy. So the other is highly associated with each other based on the promoter profile. Interesting. And what is the next? I will search around output to retrieve the expression pattern. So the problem is output is closed because of the funding. So funding is that important for the researchers. So the Arabidopsis information resource there is only alive. What is this? Genome context viewer. This is too slow. Context viewer. No, let's put the ID there. See if they have any idea. Search. So it has macrosynteny and microsynteny that actually I don't have any interest. Wow. This is not good at all. Not informative at all. Let me use Talemine. So Talemine is the bioinformatics tool to retrieve certain information. So it has Python API but I don't know what kind of information you guys have. And okay, so data source, expression. Okay, so we have expression. So it had one of the at gene express dataset or other compendia desired gene into the. So this is not RNA-seq data. What I want to have is RNA-seq data rather than other stuffs. Okay, let's go to expression atlas. So expression atlas is large database which has RNA-seq information. So usually people actually has been used array data to observe the expression, but the resolution is so far lower than RNA-seq. So people try to use RNA-seq for their own research. So of course, if you have high resolution of expression data, maybe it lose your original hypothesis because sometimes your hypothesis is strongly supported by what is that array data. However, RNA-seq data doesn't because RNA-seq data has more resolution. So the time course RNA-seq analysis Bali. So I don't want to have Bali. Then why it is okay. So this is powdery mildew, right? But I want to check if there is tissue related transcription profiling by array. So I don't want to have array. So everything is array. Experiment kingdom. So everything is so specific. I want to have more seek search all column. This is not so good. Magic line. Actually, I didn't know that autopsy experiment has this much genetics. So this is all genetics, right? So, Lirata. I don't want to have Lirata. Washer. Interesting. I really like this term, transcriptional dynamics. Yes, it is dynamic. Okay. Download expression result. row count. Let me check the design. Open up, open up, open up. Good. So this is the experiment design. So factor value. So sample is all lip. Everything is coming from lip. And factor value. And so everything. So this is all mutant analysis. I don't like mutant analysis. Is there any profile result that is try to see the transcriptional dynamics of their healthy life? Let me check one more time, and there is no good information, then I will check just anything. Okay, I will use anything. So, stomatal lineage. So it must be some single cell sequencing I don't like. Okay, so let's check if this is good or not. So experimental design is what is the Zeitgeber? What is Zeitgeber? Zeitgeber is any external or environmental cue. I don't know. So age. So along with age, I think. Right. So along with age, so after germination, and everything is coming from shoot meristem. Let me use it. So I will use the TPM data. So let me upload this data in our working directory. So working directory. So this is working directory, right? Let me open the AXP. Read CSV again. E something, okay, and set T. Maybe there is command. Command show. Expression. Okay, so we have the list of the expression. So we have the expression. So actually, I have no clue that we will have really good result. So maybe here, because here, so there is no improvement. Why? Ah. So we have to index, right? So we have to index it, index gene ID. Good. And see if this is existing. Ah. Okay. Then we can check. We can check the expression profile. So some of them is not existing. Some of them is not existing, but hold on, drop no. Let me see. Drop now and columns. Okay. PDF speed cluster map and standard scale true and expression pattern will be not so consistent each other. However, maybe these two is similar each other. So this is so interesting. This is really interesting. I will check what is the genes 8050 33180. So these two may share the profile. Let me check. Disney. 뭐야? 33180. PDF. 점이. So almost the same each other. So what was the original one? Original one is knock. So actually this is one condition. So maybe it is not so I say comparable, but if you found something is related, then it is really interesting. No. Two. Okay. Two. Mm-hmm. And this is much closer. Okay. So this and this is much closer each other, but this and this is closer than these two comparison. So it's really interesting. And I want to see what is actually happening. Because T-SNE profile is sometimes not so, let's say, that rigid. Okay, we just use this. Data frame feature to count index and values. So T-SNE profile is certain that I use actually coming from some statistics, but this is actual value, so I want to see what's happening. This was just one, and this was 4, and this was 1. Okay. So this one and this one, this one and this one, this one and this one. Why? Why it happening this way? I think we have to find some way to extract, let's say, I think we have to retry. Let me see this one also. So this conserve, so this 2 value, right? So this 2 value is well conserved. And the reason why it gave us just 1 is that the reason is different. So this implies that we have to select key features based on the clustering result. Okay, so this is more reasonable analysis, I think. Let me write down before I forgot. So what I want to say is, first, we have to cluster the expression pattern. The expression pattern is coming from specific experiment design, and so the specific environmental condition. So condition. This environmental condition coming from the design, right? So design may require different promoter composition. So what is the meaning of require in this case? The require. So certain environmental certain environmental condition may express its own specific transcription factor set. Transcription factor set. So what I mean is that if you put certain disease-related factors, then plant would secrete transcription factor that is prepared for the disease. But if you put some hormone, then the different set of transcription factor will be expressed. So that is what I'm saying. So, and the transcription factor, transcription factors require. So this is the require different set of promoter. So this is the idea. We have promoter information and we have expression pattern. Then let's cluster expression pattern first. Data frame. This one. So this one will gives you and many information, but I will use only what was that? Where is it? This one. So why? So this is our data frame. And let me check the shape. We have 10 features and we will cluster it. Let me check cluster map. Standard scale will be 0. again, it takes a lot of time. So actually, when we do this analysis in a server, it takes not this much time. I know. So something is going wrong. Something is going wrong. Let's wait for a while. Okay, so I don't think it will work. So let me change the strategy again. Let's reduce the dimensionality again. So I will remove. Ah. I think the reason why it has the error message is that some genes have identical expression pattern, so it cannot calculate the distance between them. So that's why it produced that weird error message. So what I want to do is that the clustering. No. So let me reduce the dimensionality first. Values X and PCA. Number of from cyclidron decomposition, right? So import PCA and PCA number of components with 10. I will use 10 PCA fit transform X PCA. What? Okay, so this contain none. So let me drop all none. So I don't like drop. I don't like drop. No, I don't like none. I like drop. So okay, and cluster map XPC. Let me see. takes too much time. It's just not good. So what I'm thinking is that actually I stop the analysis here. I will do this analysis in my server, and I will give you back the clustering information. So this is too heavy for a laptop, I think. So I will return you. So what I'm trying to say to you is this scheme will be happening next time. So first we have to cluster expression pattern. So we are stuck here. But once we have expression pattern and we cluster it, then we will list up the genes that we show a similar profile. And then we check what kind of promoter composition they have, and we will we will label it. We will label every genes cluster, and we will try the we will classify the cluster using promoter sequence and promoter promoter profile, and the promoter profile will gives you a good model to predict the cluster. Then what kind of feature is really important for the classification, then it will give you back the promoter blocks that is really essential for the expression pattern. So then what I'm thinking is that so the result will be different based on the expression pattern. So when you use the expression pattern from disease resistance, then you will get the promoter composition that is highly related to disease. But if you use hormone response, then you will get the promoter profile or which is really essential for the hormone response. So hormone response promoter set and disease resistance promoter set you will get. So this is that I'm thinking for next analysis. So sorry for the failing the cluster here. So this is the limitation of the laptop. So if you don't have any laptop, if you don't have any server in your environment, maybe it would be better for you to use Google Cloud. So you don't need to pay. You don't need to pay. Only you can use with Google Drive. You can use this. No. You can use the Collaboratory. So this Google Collaboratory is a free environment for you for study, and it gives you really good environment. So if you don't have this icon, then go to the app and you can search the Google Collaboratory. Yeah. It's really slow, so slow. Collab, so on collab, then you will find Collaboratory here. So you have to install this Collaboratory, then you will find here no Google Collaboratory. Okay, then you can see the environment in this way. So here, if you click on here, then it will assign you the virtual machine, free virtual machine. Even though it is free, it's not that small. So you can check here. So this free environment gives you RAM 13 gigabyte. I mean, and the disk is almost 100 gigabyte. So better than your computer, I think. So my computer is far less than this one because my memory is not that good. So the reason why this is always fail is that my memory cannot consume this data easily. So if you are interested in this analysis, then try the analysis here. This analysis, this platform gives you Python environment, so you can use any Python command here. So everything can copy paste here to regenerate the result. But the only problem is uploading the data. But if you are interested in the uploading the, I mean, no. So I want to. So I will show you. Then please refer YouTube of mine. Actually, I'm explaining how to use the Google Collaboratory. Let me show you. Video. So this must be the environment explanation for the Python. So I think it gives you the information of the right. So collaboratory. So if you are interested in using collaboratory, please refer this YouTube online. But the problem is I speak Korean. But this is okay. Just follow my command here. Okay. Thank you. I will see you next time.